Hi, everyone. I wanted to make a quick video to address a common question that I've been receiving with regards to half-lives and double times. So what I'm going to do is first, I'm just going to point out where this is in our PowerPoint lessons, but then I'm also going to do a couple more examples to just help you see how to utilize what's in our slides. So yeah, hopefully you find it helpful. So the first thing I just want to point out is that everything with regards to half-lives and double times goes back to this relationship. So this is in our module from either last week or the week before, I forget now, but the lesson is literally called half-lives and double times, so it should be easy to find. And there's lots of examples that walk you through it, showing you different hypotheticals in which you might see these words and these contexts being used. But at the very end on slide 15 is this slide. And this slide is what I call the skeleton of what all half-life and double time context ends up adhering to. So it all comes down to this relationship regarding the 1 unit change factor, whatever unit of time, and then equals 2 if it's double time, or a half if it's a half-life. Now, how you end up solving them, though, totally depends on the context at hand. So just to give you a sense of what I mean, let me share again, but this time I'm going to try to bounce over to my iPad. Let's see if this wants to be user-friendly for me. Let's see. Share and connect, mirror. Let's see. Come on. It says it's connecting. The wheels are spinning. Come on, little iPad. There we go. Okay. So the contexts in which you can see these show up, it just depends on what's given as opposed to what's not given. So for instance, all I did was I rewrote the skeleton that's on slide 15 for half-lives and double times. And let's say that you're working with a context for half-life, and what you know about the situation, let's say, is that it's a certain drug and your body metabolizes it at a rate of, I don't know, 2.3% each hour. And then the question is, what's the half-life, or find the half-life? So in this context, you're given the percentage change each hour. What you don't know is the actual amount of time, amount of hours that it takes for half of the drug to be present. So what you first need to do is take this percentage and turn it into a change factor by first realizing that anytime it's a problem about your body metabolizing a drug or medicine, that's always exponential decay. Your body processes it, let's say at 2.3% of the drug each hour. So the change factor for this will be 1 minus 0.023, which is going to be 0.977. Okay, so that's our 1 unit change factor. So now that we acknowledge, okay, I have my 1 unit change factor, I have my 1 unit change factor. What I do not know is how many hours it takes. What is the half-life time for this drug? So I know my change factor. I know my goal is a half-life. What I don't know is the actual amount of time that it takes for that to occur. And in order to solve this, well, if it was the first half of our chapter, we would have done intersect method in Desmos. But since it's the second half of our chapter, we can use logarithms. Yes, bases, powers, results. So I'm going to invert this into its logarithm form. So it's going to be log base 0.977 of 0.5 in order to get the time. And then once you know what your bases, powers, and results are, you can then just slap that into Desmos. Let me go back into this. Where are you, Desmos? There we go, Desmos. So what did we say? It was log base 0.977 of 0.5. And so we get 29.7, let's see if I round it, 29.79. So the half-life of that particular drug would be 29.79 hours. You have to make sure you always have the unit on there. And that's just completely driven by whatever your unit of time stands for. And so since our hourly decay rate was an hourly decay rate, that means that our half-life is the number of hours it takes to reach a half-life. Now, the flip side of that is, go back to my iPad. Hopefully it, no, why? Every time it's going to do this? Really? All right. Now the wheels are spinning again. I sure wish this would just be seamless. Do, 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 do. I feel like I should start singing the Jeopardy song or something. Oh, there we go. Okay. So what we say it was 29 point something. I'm not even going to dare click back over to my laptop right now, but you saw it on the Desmo screen before. So whatever that was, 20 something 0.89 is the number of hours that we found in Desmos. Okay, but what I wanted to show you is that particular example is one where you know or can easily figure out the change factor, but you do not know the unit of time. Well, other times you might be told, let's say that a certain, I don't know, population, a species, maybe it's rabbits, maybe it's insects, who knows? But let's say that a certain species, you're being told, so it's presented to you in that whatever that species is, let's say that it is told to you that it doubles every, I don't know, 7.3 years. Totally made that up, but humor me. So I'm telling you now that it doubles every 7.3 years. Well, the question might be then, by what percent does the species grow by each year? That could be a question that I would ask based on this information. So first and foremost, please acknowledge the skeleton is the same. I'm still going to be looking at the change factor raised to some unit of time. And in this case, it's a doubling time, not a half-life. So I'm going to put equals 2 instead of equals 0.5. Skeletons are the same. The only thing that changes is whether or not your goal is a 0.5 for a half-life or a 2 for doubling time. So that's going back to the skeleton on slide 15. But in this particular situation, I'm being told that it doubles every 7.3 years. The question is, by what percent does it grow? So I do not know my change factor this time. But I do know that after 7.3 units of time, in this case years, that is how long it takes to double. So this is me, again, utilizing what I know to figure out what I don't know. Now, on this particular one, in order to solve for the change factor, I just have to undo a power of 7.3. And so the way that we undo a power of 7.3 is by using its reciprocal power. So in this case, 1 over 7.3. And I'm not even going to dare go back to my laptop. I'm just going to grab my phone really quick and go to my Desmos app. And all I am typing is 2 raised to the 1 over 7.3 power. I would encourage you to grab your technology and type it in yourself to make sure that it's going smoothly. But I just typed it in my Desmos, and the answer that I'm getting is 1.0996. Okay. But again, please digest this. What I now have found is the change factor, the per 1 year change factor. But the instructions are asking by what percentage does it grow? So if my change factor is 1.0996, I'm now trying to figure out by what percent rate is that growing by. So this goes all the way back to like literally week 1 of this unit, dealing with percent change and factors. So if I know my change factor is 1.0996, the question is, what's the rate? And so if you do the quick subtract 1, 0.0996 is the percent rate. But again, remember, R always stands for the percent rate in decimal form, always decimal form. So the actual percentage is 9.6, 9.96, excuse me, percent each year. And so what you can see is every single one of these problems comes back to that skeleton. The question simply becomes, what do we know versus what are we trying to find? If you know the percent rate, AKA you know the change factor, okay, well then you're here. You know the change factor. The question is, what is the unit of time for that? And we can solve logarithms to figure that out. Other times, I will tell you the time. I will tell you how long it takes to be cut in half. I will tell you how long it takes to double, in which case your job is to figure out the change factor, maybe figure out the implied percentage. You just have to read carefully. Unfortunately, I do not have a magic wand for these or a silver bullet. Every problem is slightly different, but I can promise you it all comes back to this skeleton right here, in which case you can either use a logarithm if you have to, or maybe just use a reciprocal power to figure out the change factor. It just depends. So unfortunately, like I said, no silver bullet, but I'm hoping that that little reminder of the skeleton form itself and how to kind of, plug stuff in based on what you know, and then solve using algebraic techniques for whatever you don't know. I'm hoping that was helpful. So if you have any questions, you know where to find me. And yeah, good luck. Have fun with it. Thanks, guys.